Welcome. This is our submission for the WPI Vibe 2023 program, affordable/easy-to-use imaging device for malaria diagnosing. Our Group 2A consists of Mauricio, Lloyd, Ethan, and Vivian. Malaria is caused by a parasite transmitted through mosquitoes. In 2020, there were 241 million cases of malaria and 627,000 deaths of mostly children in sub-Saharan Africa. To prevent the spread of malaria, it is imperative to develop an affordable, shelf-stable, accurate, and easy-to-use testing device that can be widely used to detect malaria in people before it spreads. One of the most effective ways of diagnosing malaria is through a quantitative Buffy coat test, or QBC test, by identifying malaria-infected red blood cells under a microscope. For this, blood must be drawn and then centrifuged before being analyzed under a microscope. However, standard laboratory microscopes and centrifuges require electricity and are too heavy and bulky to be portable. Additionally, they are often too expensive for many developing countries.
To create an affordable electricity-free solution, we drew inspiration from Stanford's Foldoscope and Paperfuge projects. The Foldoscope, a paper microscope with a glass ball at its center, is cheap but has low magnification. To enhance its capabilities, we will incorporate this smartphone. The Paperfuge is a paper centrifuge inspired by a children's toy that creates a spinning motion reaching required speeds. While it exhibits unwanted rotation in both directions, we will not change the Paperfuge design as its affordability and lack of electricity align with our design criteria. We will improve upon the system with the implementation of AI in smartphones. This is an overview of how it should look like. After the visible Buffy coat has formed, it will be placed under the Foldoscope and smartphone for malaria detection. This is the app overview, and this is how it should look like.
You may think that using a phone as an affordable way to diagnose malaria is not feasible in many African countries, but as of 2021, it's been registered that 91 of every 100 people have a phone subscription in Nigeria. We may say there is a decent coverage of phone usage, which will only continue to increase as smartphones become more accessible. From the map, you can see the signal coverage in Nigeria. Although high-risk areas may have comparably low smartphone ownership, the design of our system only requires the person administering the test to own a smartphone. 60% of malaria patients were misdiagnosed on their first visit, and almost 19% have complications, becoming really important to get help during the diagnosis. By using smartphones, we may decrease the misdiagnosis rate by improving accessibility.
Now, traditional diagnosis of malaria requires manual identification of infected red blood cells, their species, the infection stage, and an estimation of the parasitemia charge for a correct prognostic, which relies on expertise. The automatization of this task will have a great impact in malaria diagnosis, especially in countries such as Nigeria, where the doctor-patient ratio is 1 to 9,000. On our first classification demo, we use a convolutional neural network of MobileNet version 2, which has been pre-trained on ImageNet, but only the classification layer of the model was pre-trained on a GPU for over 10 epochs, and adjusted accordingly to two classes. We applied some basic image transformations, and the model obtained an accuracy of 93%, which can be improved further by experimentations of layers, model, and hyperparameters. However, we have to take into account that we only did this to show the logic of how it would work with the demo, as this only includes the classification task and there isn't a publicly available dataset of QVC samples. It was trained on DMS10 samples, but both are markers and work in a similar way. Here we have an example of how the UI would look, given the possibility of uploading a photo or taking a photo to detect individual cells through bounding boxes and classify them by infection, stage, species, and count the parasitemia charge. Now we're going to leave you with a demo of how the classification task works. In this demo, we must consider that we're recording the samples from a computer screen. The computer and the phone camera have their own refresh rate and they are not properly synchronized, resulting in a flickering effect in the recording that causes for the model to occasionally alternate the prediction. Taking the sample directly from the microscope wouldn't induce this artifact. Finally, we have the cost. As we can see, the difference between our proposition against the traditional laboratory equipment is really great, without even taking into account the additional labor cost of microscopists. So this was all for our presentation. Thank you very much for your time.